Well, hello and welcome everyone. In this video, I decided there were several that requested, and I think some that could benefit of me going through this LEAP 2025 geometry practice test that is on Edulastic as we prepare for the LEAP 2025 geometry test. So I'm going to go and jump into it. And let's just get rolling with it. So number one says select from the drop-down menus to correctly complete each sentence. It says the set of all points in a plane that are equidistant from a given point is called a blank. So let's go and see what the options are. A square, a sphere, a segment, a circle. So it says the set of all points in a plane that are equidistant from a given point. So one of the unique shapes we have, and I know often students, they typically want to say square here, but that's because all sides of a square are the same length. But there's a really unique shape in geometry that its characteristic, or it has its properties based on this idea that all the points on that shape are the same distance from a given point. So what makes a circle round, as we call it, is that, and by the way, when I draw a arc in this case, and that's what this circle is technically, it's just a bunch of points, a bunch of tiny little points next to each other, an infinite number of points, in fact. And so what makes a circle round, as we describe it to be round, is that all of these points are the same distance from one point in the middle. We call the center. So the set of all points in a plane, and a plane, you've heard the coordinate plane. It's often just a two-dimensional surface. That's all it is. So just think of a sheet of paper as a plane. So the set of all points in a plane that are equidistant from a given point is called a circle. And the given point is called the center of the circle. So that is simply a vocabulary definition based on geometry. So let's go move on to the second question. So number two says in the coordinate plane, line P has a slope of 8 and a y-intercept of 0, 5. Line R is the result of dilating line P by scale factor of 3 with center 0, 3. What is the slope and y-intercept of line R? So one of the interesting things here is that when we dilate a shape in geometry, is that it does not turn, rotate, or reflect that shape. So for example, if we had a square and we were to dilate it, and I'll go and label these points here, and if we were to dilate that square, let's say, a scale factor of 3, so each side length will be 3 times larger, so we can call that A prime, B prime, C prime, and D prime. The interesting thing about a dilation is that corresponding segments are actually going to be parallel to each other. So that AB, this segment right here, is actually going to be parallel to line segment A prime, B prime. And one of the key characteristics of parallel lines is that they have the same slope. So for starters, if line P has a slope of 8 and line R is a result of dilating line P, then line R also has to have a slope of 8. So let's go and look through our choices. It says A says line R has a slope of 5, so it's not that one. Line R has a slope of 8, so it might be this one. C says line R has a slope of 8, so it might be that one. And D, line R has a slope of 11, so it's definitely not that one. So now we need to determine which option it is, either B or C. So think about this, and just even the diagram that I have here, if we dilate a line or even a shape where the center of that dilation is not on the line segment, that's the important part here. So 0, 3 is not going to be a point on line P. So because the center of dilation is not a point on line P, it's going to shift line R to a new location. So it's not going to have the same y-intercept as line P. So if you notice on B, it says it has a slope of 8, but the same y-intercept as line P. So our best guess right here is that C, line R, has a slope of 8 and a y-intercept of 0, 9. Okay, so let's move on to the next question. Oh, I see it actually wants me to select that. I don't know why I didn't even think to do that there. So number 3 says the equation x squared plus y squared minus 4x plus 2y equals b describes a circle. And it says part A, determine the y coordinate of the center of the circle and enter your answer in the box. So the standard form of the equation for a circle, just like the standard form for, let's just say the standard form for the equation of a line is ax plus by equals c. That's the standard form equation of a line. Now, dealing with a circle, it's obviously a little bit more complicated. The standard form for the equation of a circle will be ax squared plus by squared equal r squared. I apologize, I misspoke there. It's some form of this. I forgot that there are binomials involved. It would actually be x minus a squared plus y minus b squared equal to r squared, where a and b are actually the center of the circle. So it's the coordinate a comma b, and r is the length of the radius. So this is standard form of a circle. So what we're going to do, because we need to find the y-coordinate of the center of the circle, is we're going to write this equation in standard form so that we can find the y-coordinate, which is b, for the center of the circle. To do that, we're going to perform something called completing the square. It's a pretty intense process, especially when we don't have this y term here. It's a pretty intense process to solving quadratics, much less circles. So if you need extra practice, feel free to find other resources to do that. But we're going to take a look at writing the standard form of a circle given this equation. So I'm going to go and rewrite that at the top. So x minus a squared plus y minus b squared equal to r squared. So to get in that form, the first thing we're going to do is rewrite this equation where we have our like terms somewhat next to each other. So for example, I'm going to keep x squared first, and then instead of going ahead and writing y squared, I'm going to go ahead and bring that negative 4x over next to that x squared term. So then we can go and write the y squared term plus 2y equals b. So this idea of completing the square involves something called perfect square trinomials. In fact, a perfect square trinomial is the result of a binomial squared. So what we're about to do is take these two terms here, which are only two terms, and turn them into what's called a perfect square trinomial. In other words, we're going to create a perfect square. So to perform this, we're going to add, we're going to bring down x squared minus 4x, and we'll write plus blank. We're going to literally complete a square, and then bring down the y squared plus 2y, and do the same thing here, write plus blank, because we actually need to create a perfect square trinomial for both the x term and the y term. And set it equal to b plus, and we're going to I'm going to show that whatever I add to this left side, I have to add to the right side as well. So whatever I write here, I'm going to put in this blank, and whatever I put here, I'm going to put in this blank. So to find the value that goes in this blank, you're going to take half of this value here, which we call b. So if you recall, standard form of a quadratic, it's ax squared plus bx plus c equals 0. So, and if you notice, that's what we're really doing. We're writing a quadratic. So we're going to take half of this value, so it's b over 2, and then square it. So we're going to take half of negative 4, which is negative 2, and then square it and give us 4, positive 4. And that's what we're going to put in this first blank. And of course, we're going to have to add it in over here as well. Then we're going to do the same thing with this perfect square trinomial with our y value. So we're going to repeat the process. So we're going to use this 2 as our b. So 2 divided by 2 is 1, and 1 squared is 1. And again, we need to add it to both sides. So the reason we wrote x squared minus 4x plus 4, the reason we did that is we just turned that into what's called a perfect square trinomial. In other words, it's a binomial squared. The same way, 9 we call a perfect square because it is 3 squared. So we're going to take this perfect square trinomial and write it as a binomial squared. And we're going to do the same thing with our y term as well. So a binomial squared. So to find the pieces that go in our binomial, there's a kind of memorization here. We're going to take the square root of the first term and bring it down. So the square root of x squared is x. We're going to bring down the first sign, that's pretty important, and then we're going to take the square root of the third term. Then the square root of 4 is 2, and we bring that down. So if you learn the process of actually squaring a binomial, if you took x minus 2 and squared it, you would actually get this trinomial. So we're creating just a new equivalent equation, representing it as a binomial squared. And we're going to do the same thing to our y term. So we're going to take the square root of our first term here. So the square root of y squared is y. Bring down the first sign, and then take the square root of our third term and bring it down. And the square root of 1 is 1. Now we can go and finish out the rest of this equation. We can't literally add b plus 4 plus 1, but we can add 4 plus 1. So simplifying this right side, we would at least have b plus 5. So we have written this in the closest form we can because we don't exactly know what b is here. But we do have the equation that can reveal to us our center. So if you go back and notice the standard form for a circle, a little bit untraditional, it's x minus our x coordinate for a center and y minus our y coordinate for the center. So the way I view it is that our center, the location of our center, is the opposite sign of what I'm seeing here. So if it's x minus 2, the x coordinate for our center is positive 2. And if it's y plus 1, the y coordinate for our center is actually negative 1, because it would truthfully be y minus a negative 1. So our center is 2, negative 1. And so all they've asked for us on part A, or at least in this box, is to input the y coordinate. So we're dealing with a negative 1. Let me scroll down, see if there's any other parts. I figured there would be a part B. So now it says the radius of the circle is 7 units. What is the value of b in the equation? So if you go back to standard form, which we are nearly in down here, is it's x minus a squared plus y minus b squared equal to r squared. So whatever all this nastiness is set equal to is actually the length of our radius squared. So if it tells us that the radius of the circle is 7 units, they're telling us the length of the radius is 7 units. What's the value of b in the equation? So if the length of our radius is 7, then this term right here should be 7 squared, which is 49. So we need b plus 5 to equal 7 squared. Or, in other words, 49. So to solve for b, we simply subtract 5 from both sides, and b will equal none other than 44. So let's go ahead and put that in that part b there. I don't believe there's any other parts to this one, so we'll go and move on to the next question. So number 4 says the figure shows triangle ABC is similar to triangle DEF with side lengths as indicated. So remember, with similar triangles, corresponding angles are congruent and sides are proportional. So without getting too far into it, let's just see what the question actually wants us to do. So they ask us, what is the value of x? Enter your answer in the box. Let me get some of this stuff out of the way. So if they want us to know the value of x, x is representing a side length on our larger triangle, ABC. So we're using the idea that for similar triangles, sides are proportional. So I'm going to look to the statement. I love using the statement to really make sure which sides are corresponding. Remember, the order of the statement actually tells me which sides are corresponding, and that's going to help us to write a proportion to solve for x. Now, there's another way you can do this. Of course, if you figure out the scale factor, that's one way that you can approach this one. I like using proportions, so that's the way I'm going to show it. So we definitely need to find the length of CB. Let me pick a better color than that, one that you might be able to read. So let's figure out, when writing our proportion, what CB corresponds to. Now, if you notice, they oftentimes will rotate the figure that it's similar to try to throw you off. So that's why I really rely on the statement. So looking at the order of the statement, BC or CB is the last two vertices in the first triangle. So that means it corresponds to the last two vertices in the second triangle. So BC should correspond to EF. So CB will correspond to FE. Now you might have figured that out, but just for the sake of rotations, possible rotations here, we don't want to get that messed up. So to finish out the rest of our proportion, if I started with a segment on the large triangle and went to the smaller, then what I have to do for the second part of my proportion, in the numerator, I have to write another side of the large triangle. Now, fortunately for us, we have all the measurements for the small triangle, and we have the two others for the large, so it really doesn't matter which other side we choose. So I'll just choose AC. And so if CB corresponded to FE, now let's see what AC corresponds to. So AC, looking at the statement, A being the first vertex and C being the last, corresponds to segment DF. So AC corresponds to DF. So now I'm going to replace my segments with known values. So CB we're going to replace with X, obviously. FE we're going to replace with 5. AC replace with 27. And DF with 9. Now, obviously, this is not the only route to take here. There's many other proportions you could have written, but this is the set that I chose. Now, even at this point, you might be realizing, well, 27 is 3 times the size is 9, so X should be 3 times the size of 5. Of course, if you can see that, you don't need to go any further. But we love proportions because maybe it's not that obvious. And if it's not that obvious, we can use a simple technique of cross multiplication to find the exact same thing that you were probably thinking. So we'll multiply 27 times 5. Which is 135, and 9 times x, which is 9x. Then divide 135 by 9 to solve for x, and we get probably what many of you were thinking, x equals 15. So just using a proportion here, you could have used a scale factor if you prefer. The value of x is 15. Let's go and move on to the next question. Number 5, it says in the figure shown, line CF intersects line AD and line EH at points B and F respectively. So it says part A, given angle CBD is congruent to angle BFE, and our task is to prove angle ABF is congruent to angle BFE as well. So we are dealing with a proof. So let's look at what we have here. It says select from the drop-down menus to support each line of the proof. So what I'm going to do is just simply, so I can kind of work through this proof, I'm going to kind of quickly just draw what we have over here. Please ignore the crude drawing, or not crude, but the rough drawing here, just so I can scroll down and we can still see the drawing. So we are given that angle CBD is congruent to BFE. So I'm going to go and show that by marking these two. And our task is to prove that angle ABF, which is right here, is congruent to BFE. So let's see if we can figure that one out. So let's see what the proof has for us. So our first statement says angle CBD is congruent to angle BFE. So let's see what possible reasons could be. And let's see, they are kind of out of sight here. Given definition of congruent angles, vertical angles congruent, reflexive property of congruence, symmetric property of congruence, and transitive property of congruence. Well, how do we know that angle CBD was congruent to BFE to begin with? Well, it was given. So the simple answer here is that angle CBD is congruent to BFE because it is given information. Now let's look at why they would make the claim that angle CBD is congruent to angle ABF. So that wasn't given to us. So there's got to be a reason that they are telling us that angle CBD, I thought I was going to mark, angle CBD is congruent to angle ABF. So let's look at the possible reasons. Probably a lot of the same reasons. If they use the word congruent, students typically will say, well, definition of congruent angles. Well, definition of congruent angles just says that they have the same measure, and that's not what we're saying here. Why are these two angles in particular congruent? Well, it wasn't given information. It's not the reflexive property. It's not the symmetric property. It's because they are, in fact, vertical angles. So when two opposite angles are formed by the intersection of two lines, so look at angle CBD and angle ABF. They are two opposite angles formed by the intersection of lines CG and AD. They are congruent, actually referred to as the vertical angles theorem. So how did I know that angle CBD and angle ABF are congruent? Because vertical angles are congruent. Now let's look at our next statement. Now it says that angle ABF is congruent to angle BFE. So this is actually our final statement that we're looking for, that we're trying to prove. So if we say that angle CBD is congruent to BFE, and CBD is also congruent to ABF, then by what's known as the transitive property of congruence, ABF also has to be congruent to BFE. For example, if CBD was 70 degrees and they told us that BFE was congruent, then it's also 70 degrees. Well, we just established that CBD and ABF are congruent, so ABD or ABF has to be 70 degrees. Therefore, ABF and BFE have to be the same measure. That's what congruent means. So they are the same measure or congruent because of the transitive property of congruence. When two angles are congruent to the same angle, they're congruent to each other. That's the transitive property. Now let's take a look at part B. Looks like we have another proof here. So let me see if I can clean up our diagram just a little bit without having to redraw it. save a little time. Redraw that B in just a second. Okay, so it says given the measure of angle CBD is equal to the measure of angle BFE. So these two angles have the same measure, which actually really does mean that they are congruent. So I'll go and show that there. And our task is to prove that the measure of angle BFE, that angle right here, can add to the measure of angle DBF and somehow equal 180 degrees. So let's take a look at our statements. So the first statement they tell us is the measure of angle CBD is equal to the measure of angle BFE. Well, where did we get that? How did I even decide that these two angles were congruent? Well, some of you might be saying, well, it's because they're corresponding angles. But we don't even need to make that claim, and they didn't even tell us that the two lines were parallel. They told us from the beginning that CBD, the measure of angle CBD, is equal to the measure of angle BFE. So that reason is given. So don't overcomplicate these proofs for those that are working on them. Next, it says that the measure of angle CBD plus DBF, the measure of angle DBF, is equal to 180 degrees. Well, if you notice, that wasn't given information. So we must be looking to the diagram to figure out why those two angles should add equal 180 degrees. So CBD, angle CBD is right here, and angle DBF is right here. So why are we supposed to know that these two angles in particular should add equal 180 degrees? Well, it's because they form a straight line together. These two angles, this acute angle and this obtuse angle, when combined, actually create 180 degrees or a straight line. This has a very particular term in geometry. Let's just look at the reasons, make sure that that is actually there. Angles that form a linear pair are supplementary. Angles that are adjacent are supplementary, not always. Reflexive property of equality, nope. Substitution property of equality. Well, if you forgot, supplementary means two angles that add equal 180. So it's either angles that form a linear pair are supplementary or angles that are adjacent are supplementary. Well, not all angles that are adjacent have to be supplementary. In fact, angles that are adjacent could be complementary. So angles that form a linear pair are supplementary. A linear pair refers to two angles that form a line together, and that's how we describe measure of angles CBD and DBF. Last and certainly not least, we have the statement that we're trying to prove. Measure of angle BFE plus the measure of angle DBF equals 180 degrees. So statement one, they tell us that the measure of angle CBD is equal to the measure of angle BFE. And in statement two, I mentioned measure of angle CBD again. Well, if I have already established that measure of angle CBD is equal to measure of angle BFE, I should be able to replace measure of angle CBD with BFE in any equation. So what I'm going to do is now replace measure of angle CBD with its equal angle measure BFE, and now have the equation that I was trying to prove. Now, when you replace something of equal value in the equation, it's referred to as substitution. Just like in algebra, when you solve for x and you put that value back into the equation, it's called the substitution property. So hopefully they have that on our drop-down menu, substitution property of equality. Very good. So a little work with proofs there. I know it can be difficult for some, but just working through what's given, what the diagram shows us, and what the rest of the proof gives us. Let's move on to our next one, question 6. So it says point Q lies on line ST, line segment ST, where point S is located at -2, -6, and point T is located at 5, 8. If SQ to QT is 5 to 2, where is point Q on line segment ST? So this is a ratio right here comparing the lengths of SQ to QT. So they're not really saying that the length of SQ has to be 5 or the length of QT has to be 2, but that the ratio between the two line segments has to simplify to 5 to 2. So just dealing with integers, SQ could be 10 and QT could be 4, or SQ could be 15 and QT could be 6. But that's really just primarily looking at integers. It could be anything as long as the ratio can simplify to 5 to 2. So we're talking about distance here. So it says select the point and then select the place on the coordinate grid to plot Q. So our task is to find out where point Q will end up if the ratio between those is 5 to 2. So let's go and label here. So S is located at -2, -6. So this is S down here. And this must be T up here, which is located at 5, 8. So I'm going to show you two approaches to this one. One probably definitely more complicated.
Miss Jasmine Lewis, bus the office, please, Miss Lewis.
Sorry about that. One definitely a little bit more complicated, but more mathematical in its mindset. But then the other one just kind of looking at the picture and figuring out how the ratio 5 to 2 really works. So we'll start with the easy process, and then we'll show the more mathematical way. So if the ratio is 5 to 2, then we're really talking about a total of 7 parts. So what I'm going to do is I'm going to divide this segment into 7 equal parts. So if you notice the way this line segment is drawn, that if we go up 2 units and right 1, we end up back somewhere on the line and also on the grid of our coordinate plane. So I'm going to divide a section here, and then I'm just going to repeat that process. And it'll actually give me 7 parts. So 1, 2, 3, 4, 5, 6, 7 parts. So the ratio of 5 to 2 means for every 5 units that the distance from S to Q is, Q to T has to be 2 units. So we have from here all the way up to this point, that's 5 units, if you will, not exactly units on the coordinate plane, but 5 sections, and 2 sections. So what that means is that Q is actually going to end up here at the point 3, 4. Now, that is a pretty easy approach, and I can't always guarantee that it'll work that way. I'm going to show it to you the other way using the distance formula, because that is also what is at play here. So to find the...
Mr. Park,
my goodness.
The office. Mr. Park.
Sorry about that. Sorry about my reaction too. It's just a little bit rough on that end. So we're going to find the distance between S and T. So the distance from our x's, x minus a -2, or 5 minus a -2 is 5 plus 2 squared, plus 8 minus a -6, which is 8 plus 6 squared. We'll get 7 squared and 14 squared. Square each of those and get 49, and I believe 14 squared is 196. Add those together, and we get the square root of 245. Well, that doesn't seem like it could help us, but if we actually simplify that square root, it's actually going to help us a great deal. So the square root of 245 is 49 times 5. If you were to take 249 or 245 and divide it by your perfect squares, the largest perfect square that can divide into 245 is 49. So we're going to take the square root of 49, it being a perfect square, square root of 49 is 7, and leave our non-perfect square inside the square root. So how does that help us? Well, go back to what I was referring to about the 7 parts. So the length from S to T is 7 times the square root of 5. So 7 times the square root of 5. So if it's a matter of 5 to 2, then from S to Q, we should see 5 times the square root of 5, and from Q to T, we should see the other two parts, 2 times the square root of 5. So I'm looking for 2 times the square root of 5 in distance. Well, some of you are probably still asking, well, how does that help us? How do I know what 2 times the square root of 5 is? Now, this method, again, I've already shown you a pretty easy way of tackling this. This method is definitely more math-minded. And there might be an easier method out here. I can't say that I'm the best mathematician here, but this is one way that I'm working through it. So I'm really looking from T to Q, 2 times the square root of 5, which is 2 times the square root of 5 is the same thing as square root of 20. And so the square root of 20, possible ways that we would even get the square root of 20 is, let's say, square root of 16 plus 4, these two perfect squares. And the square root of 16 is 4, and the square root of 4 is 2. So I'm really looking for a distance between 4 and 2, either vertically or horizontally here. So if I notice from here to that point that I imagine, the distance from T down is 4 units and over is 2 units. So this is just another way, and if you were to do the Pythagorean theorem with 2 squared plus 4 squared, you would get the square root of 20, which is 2 times the square root of 5. So I would imagine that most of you are going to hang your hat on using the 7 parts here, and that is definitely doable, but I wanted to show a little bit more mathematical way to do that. So the last thing we need to do for this problem is actually plot point Q. So I'm going to go and select point Q, and then I'm going to go and drop it in at point 3, 4. Now let's move on to the next question. Number 7 says the circle with center F is divided into sectors in circle F. In circle F, line segment EB is what's known as a diameter, and the radius of circle F is 3 units. So we're dealing with circles here, and it says to drag and drop each arc length to its subtended central angle. So there is a mathematical connection between a central angle and its arc length. Okay, so the first thing we need to look at here is if you notice that it says arc length in radians. What typically students know of in terms of circles is degrees. And so I'm going to show you a quick way to go from degrees to radians for starters. Degrees to radians. So degrees, we primarily use degrees to measure angles. And as you notice here, we have angle AFB, which is 120 degrees, angle BFC, which is 45 degrees, and angle CFD, that is 30 degrees. Radians, we typically use to involve the measure or the length of these arcs around a circle. It involves the term pi, which we use this symbol for pi. That's it's a number that never ends. Most students know pi as 3.14, but it actually continues on forever. That's because a circle is actually made up of an infinite number of points that are all the same distance from the given point, called the center. So the first thing I'm going to show you how to do is convert these angle measures, for starter, convert these angle measures to radians. So to quickly explain this concept here, what we're really looking at is the total distance around a circle. That's what we use. We typically involve radians and pi when we start talking about the length around a circle. So if you recall that the total distance around a circle is known as the circumference, and the circumference formula is 2 pi r, where r is the length of our radius. So for a circle that has a radius of 1, the circumference would be 2 times pi times 1, which is 2 pi. So the total distance around a circle is 2 pi radians, or if we're talking about it has a radius of 1 unit. And obviously, they told us that the radius of the circle is 3 units. So if the total distance around a circle that has a radius of 1 is 2 pi, then half that distance would be 1 pi. Well, half of a circle in degrees is 180 degrees. So when converting degrees to radians, we are going to multiply our angle measure, which we usually involve this Greek letter, which is theta. It's not just a circle with a line through it, it's actually a Greek letter called theta. We're going to multiply theta, our angle measure, times pi over 180. Because pi and 180 degrees are actually the two different ways to measure the same thing. Well, not necessarily the same thing, but the same area, if you will, or section of a circle, 180 degrees as the angle, or pi as the radian length of that angle measure, 180 degrees. So we're going to go and convert all of these angle measures to radians by multiplying that angle measure times pi over 180. So multiplying 120 times pi over 180, I'm going to put 120 over 1 because I'm multiplying by a fraction, and I will get 120 times pi, which we'll leave it as 120 pi. If you notice, the answers are still involve pi, so we won't multiply by 3.14 over 180. Now, 120 and 180 can divide by a common factor, so we're definitely going to do that here. Always simplify your fractions as you can. So I believe both of those can divide by 60. So 120 divided by 60 is 2. Goodness, I'm getting ahead of myself. 2, so 2 pi, and 180 divided by 60 is 3. So I'm just going to write next to this, AFB is 2 pi over 3. So 120 degrees as radians, which again is representing the arc length, is 2 pi over 3. But it's not exactly the arc length. I want to keep that in mind because we're on the understanding that when converting to radians that the radius is 1. We're going to handle when we actually talk about arc length in just a second. So now let's go and convert the angle measure for BFC. So we're going to take 45 and multiply by pi over 180. And just a quick fact here, if you want to go the opposite direction to convert from radians to degrees, you just literally flip pi over 180 to 180 over pi. So we'll put this over 1, multiply, get 45 pi over 180, and then see if there is a common factor between 180 and 45. And I actually believe it is 45. So we're going to divide top and bottom by 45. When we divide the top by 45, we get 1. So we'll get 1 pi, which we could just write pi. And 180 divided by 45, we get 4. So 45 degrees in radians is pi over 4. Last and certainly not least, just converting angle measures to radians. We're going to do 30 times pi over 180. So if you can't tell, all we're really doing is finding the common factor between the central angle and 180 degrees, which I believe it's going to be 30 for 30 pi over 180. Absolutely it is. So this will simplify to pi over 6. So we just converted the angle measures in degrees to radians. So the next thing we have to do to actually calculate the arc length is then take the measure of the angle in radians and multiply it by the length of the radius. Again, we came up with this concept of degrees to radians based on the radius being 1 here. That's why we went from 2 pi r to simply 2 pi, because multiplying by 1 doesn't change anything. So if the radius is 3 units, to find, I don't know why I'm grabbing that, to find the arc length, we're going to take the measure of the angle in radians, and we're going to multiply it by the radius. So we're going to multiply this by 3, this by 3, and this by 3. So 2 pi over 3 times 3 will equal 2 pi. Pi over 4 times 3 will equal 3 pi over 4. And pi over 6 times 3 will equal 3 pi over 6, but that can simplify to pi over 2, or 1 pi over 2. So now we need to find their appropriate answer over here and drag them over. So angle AFB is 2 pi. So I'm going to have to erase all this, but hopefully I can remember it. So AFB is going to change. Let me just use my mouse here. Is 2 pi. Let's see, I believe BFC was 3 pi over 4. And CFD was pi over 2. Which we didn't actually find the arc length in radians for angle AFE, but let's just understand why it is just pi real quick. So we see that if EB is a diameter, then it forms a straight line through our center of our circle. So if angle AFB is 120 degrees, then angle AFE has to be 60 degrees. So if we were converting 60 degrees to radians, we'll get 60 pi over 180, and then we'll simplify that by dividing 60 and 180 by a common factor, which will be 60. So we'll be left with pi over 3. So angle AFE in radians is pi over 3. And then, like we said, we have to multiply that measurement in radians times the radius of the circle, which is 3 units. So if we multiply it by 3, the 3's cancel and we're left with simply pi. So the measure of angle AFE is pi. So we're going to go and drag that into place here.